All right. Good afternoon, everybody. Hope everybody's doing well. So we started on DC circuits on Tuesday, and today we will wrap up DC circuits. There are a couple of things we have not talked about. There are we got to talk about what the actual mechanism is, or how to quantify what those energy losses are. Remember, we worked out what that potential circuit diagram looked like when you take an imaginary stroll through the potential landscape in a closed path through a DC circuit. All the voltages that, all the voltage additions and all the voltage drops, they all need add ups to zero. And then I talked about batteries, and I talked about resistors and losses, but we haven't actually talked about how to quantify those losses. Batteries we will not get into because that's electrochemistry. There is an alternative for getting an electromotive force, and that is, for instance, by running a wire through a magnetic field, and that is something that we will cover, but that's going to be further down the line. We should start talking about another circuit element. So in addition to wires and resistors, there's another circuit element called a capacitor, and this is the moment in which we need to describe what it does and how it's used. Then capacitors are a little funny, and this is where, when we start talking about charging and discharging, strictly speaking, we're not talking about DC circuits anymore because the current is changing. But if you want to be pedantic, you could say that any DC, an absolute DC circuit does not exist, because there's no circuit that will last the entirety of the universe. So there's always a finite time. At some point, somebody must have turned the battery on, and at some point, somebody must have inserted all the wires. So we'll say it's DC, but it's actually quasi DC, because we also turn stuff off before you go home. And then that will be the end of chapter 2, and then we'll go into chapter 3, and then we'll start talking about magnetism. So chapters 1 and 2 is all that is on the first midterm. The homework set on chapter 2, so on DC circuits, is due pretty soon, and we'll make sure to get that graded and get the solutions to you before the midterm. Before the midterm, I always have a review session, and we'll do that too. Okay, continuing on DC circuits, power consumption. So in resistors, we have Ohm's law. So R is V over I, and we have a associated circuit element that is this way, and then if the current's going this way, then voltage goes down, right? So voltage is decreasing, and that voltage decrease is given by this current, and this current is, of course, dq dt. And now the question is, how can we quantify the power that's dissipated? Well, we could do this. We could do this in the following manner. So, the number of charges that go through the resistor per unit time is I. So if we take I and we multiply that by whatever energy is lost when it goes through the resistor, we should have a way to quantify that energy loss. So we need I times something. Now that something comes from the voltage, because the voltage is units, right? Is joules per coulomb, right? Because the voltage was defined as U over Q, right? So U over Q, little q, big Q. Let me make it big Q. U over Q. So that's joules per coulomb. So in other words, if you take the voltage, which is in joules per coulomb, and you multiply that by something that is coulomb per time, you're going to get joules per time. So the product of those, P, V times I, is going to be the power loss, and its units will be watts. Watts. And watts, has another unit, it's joules per coulomb, or if you want to do Newton meters per coulomb. But watts are the thing to talk about. So these are the watts that you hopefully have seen written on all sorts of electrical equipment. If you have a if you have a charger for your cell phone, it will tell you how many watts it can deliver, and basically that means how many joules per coulomb, sorry, joules per second. Sorry, how many joules per second it can deliver. All right, so that's watts. So we can calculate that in this manner, and then of course there's Ohm's law, and then there's P. So we can actually rewrite this as using Ohm's law, R times I squared, or we can rewrite this as V squared over R. All right, so that's the power consumption. Now, the actual power consumption is a function of what this material does with it. So I mentioned that what happens is there's a process in which this energy loss here gets converted to heat, for instance, and this is how tea kettles work. You know, a really straightforward tea kettle. What it is a really big wire with a lot of resistance that you run a lot of power through, and all of that power gets dissipated in the heater, and that heater is immersed in water, and that's how you get your water to boil. It's a surprisingly simple way of doing things, and it's not too bad in terms of efficiency. There are probably more efficient manners, but it's nice, you know, you plug something in, it warms up. So that's how water kettles work. Now, the type of material that you choose is going to determine how big this resistance is going to be. Not just the type of material, but also the geometry of whatever this block of material is. So let's talk about the most simple case. Let's say we have some kind of a wire. And we're giving it a length L, and giving it a cross section A. And now we're going to ask ourselves, okay, what's this resistance? Well, let's look at some scaling behavior. If we have, let's say, a wire that is 1 meter, and then we take another wire that's another meter, and we put it right behind it, now we have 2 resistors in series. So because it's 2 resistors in series, their resistances would add. So we would have the total resistance of this wire would be this one plus that one. And if it's not 1 meter that we add, but we add 2 meters, for every meter that we add, there's another whatever unit of this is. So this resistance has to therefore be proportional to the number of meters that you have in the cable. So we know that R is proportional to L. Similarly, if I take one wire like this and I take another wire and I put it underneath it, now I have 2 wires that are in parallel, and if the 2 wires are in parallel, they share the current, which means that the voltage is lower, but the resistance of the 2 is, so the voltage is the same, but the resistance is lower by half, right? Because they share the current. So no matter what that A is, if we double A, the resistance need to go down with the cross section. So therefore, it's proportional to L over A, and the proportionality constant we call rho, and rho is a is a material constant. So rho is the resistivity. And units of rho, let's see. So this is in ohms, this is in something, this is in meter, this is in meter squared. So this is in ohm meter over meter squared. So this is in ohms per meter. And that's a material constant. So once you have a once you know what that rho is, then you can calculate what your resistance is. If I'm not mistaken, you should have had a lab with the steel wire where you had to determine Ohm's law for a steel wire, and you had to independently determine that indeed the resistance scales with length. And now you know why, because of course it's a consequence of the fact that series circuits just mean that you keep adding the resistances. So all of those things are supposed to hopefully now make a little bit more sense. Meanwhile, I'm trying to look up some numbers because I forgot to write them down. There we go. So so the resistivity for copper, for instance, rho for copper is let me see, it's 1.7 10 to the minus 8 ohm per meter. Oh, it's ohm meter, sorry. Ohm meter. Sorry. Yes. Right, because you have ohm meter times meter over meter squared, so that gives you ohm meter squared over meter squared gives you ohm. Yeah. Okay. Ohm meter. So let's take an example. So let's say a cylindrical wire. So length, let's call it 10 meters, and let's take a diameter of 1 millimeter. What is R? And I'll let you work on that a little bit. Something like that. This is a thing that I always do before I start punching numbers into my my calculator. I'll gather my factors of 10 first, and then I'll gather my prefactors. Oftentimes you'll see sort of where the number is going to go. 4 over pi is going to be a little bit bigger, so that 1.7 is going to get a little bigger. Let's call it 2. So probably something like this. I'm not sure what the exact number is, but the rest is just putting it in the equation. Of course, there's a 1 over d squared. That's a millimeter. That's 10 minus 3. But once it comes on the numerator, it's squared. The exponent, of course, inverts. So you get a plus 6. So minus 8 plus 1 plus 6. So that's a minus 1. So that's where I get my 10 minus 1. Done. All right. There's an associated quantity, and that's called the conductivity. I'm going to draw this here because I want it on the same slide. So sigma is 1 over rho. Sorry, sigma is by definition 1 over rho, and therefore the units of sigma are 1 over ohm meter, and sigma is called the conductivity. And There's another unit that we sometimes use, and that's the unit of 1/ohms. And it's the capital S. I don't use it a lot in class because the capital S is easy to confuse for the lowercase s in seconds. So you know, people don't like to get confused, those two obviously. So there's a S for Siemens. So using that, you can redefine this as Siemens per meter. There you go. So that's all you need to have to understand power dissipation in conductors. Now, I mentioned before that there are materials where the resistance goes to completely zero. So, for instance, mercury is one. In fact, there was a laboratory in Leiden, which was right next to where I was doing my my undergraduate research, where they discovered superconductivity. It's a really cool place to be, and it was in mercury actually. So you cool it down to, I think, 2 Kelvin, then it becomes superconducting. I don't even remember if it was 2 Kelvin. Anyway, quite cold. Now we know how to quantify the resistance because we have this number resistivity, but underneath this material quantity, there's a whole bunch of stuff. So when electrons move through materials, they can scatter off impurities, they can scatter off of lattice vibrations. There could be bends and nicks. There could be grains that make poor contact. So this is the study of what this resistivity is an entire field unto itself. And there are temperature dependencies. So for instance, there's this very famous standard called the Platinum 100 standard, which is a resistor made of platinum. And you start with a resistance of 100 ohms, and the temperature dependence has been calibrated super well. So you just stick that in whatever you're trying to cool down. You measure the resistance. You know what the temperature is. So that's a whole field unto itself. If you want to know more about that, take a course in solid state physics, for instance. For the physics majors, there's a 400 level class for that. All right. Is power consumption. So next up, more advanced circuits. So there was this circuit that I was doing at the end of class. So let me pull it up. It was a little bit tricky. All right, you remember this one, this monster. But it was ultimately, it was possible to solve this circuit because we could work out this circuit in terms of parallel and series configurations. And then it's just a matter of relating all of them, and there's usually only two unknowns. There's a current that you need to figure out, first current, and then the second current follows from it. So it's really not too complicated. It's just a little bit, it's a little bit of a puzzle, and any kind of mistake you make kind of trickles down through the rest, and that's why you want to usually go back and make sure that these diagrams still make sense. But what do you do if you cannot use series or parallel configurations? And now you might be shocked, Professor Postma, how could that possibly be? Well, it's not that hard to make this into a circuit. You can't use parallel or series configurations. So for instance, if I do this, right? So I add a power supply here, that now makes it impossible to say what is in parallel and what is in series. So there's a different approach that we have to use for this kind of circuit. So let me explain to you how that works. So I'm going to start with the most basic version of a circuit that you cannot decompose into parallel and series configurations. So that would be two power supplies, some resistors, and a resistor in the middle. All right, so let's call this advanced circuits, even though I like calling it advanced circuits because it makes it feel super advanced, but it's probably a misnomer. Okay, so the most simple version of that is as follows. So we have one resistor here, one resistor here, and one resistor here, and a battery here. All right, now let's say all I would like to know is what is this current going to be? It's reasonable to assume that this current is going to go down through this middle resistor because this battery is sourcing a current in this direction. This battery is sourcing a current in this direction. So it's entirely possible that if you have these two currents coming together, that's reasonable that this current would be going down. So I'm taking a step ahead and say, you know, it makes a lot of sense to expect something like this. But now, how would you solve this? So there are the two rules that that you use to solve these circuits. So rule number one is charge conservation. So charge conservation is a bit of a funny concept because I've talked about creating positively charged objects and negatively charged objects. What we mean by charge conservation is that if you charge an object positively, that means that you've removed negative charges. You might have removed them from that conductor, but they're not gone from the universe. So the same thing here. We know that we cannot charge this thing. Whatever goes in must come out. So that means that the net current at a junction equals 0. Or if you want to call it other way, I in is I out. Or if you want to be fancy, sum of the current vectors is 0. Or if you want to be super fancy, that's a Gaussian type integral. These are all the same things, right? So whatever current goes in must be equal to the current that goes out, because inside this volume or at this node, we cannot store charge. So this is Kirchhoff's current law. And the second one we already had established, and that was the sum of voltages in closed loops is 0. So that would be sum of voltages is 0, and that's of course the Kirchhoff voltage law. Okay, well let's put some numbers here. So let's make it super simple. Call this 1, call this 1, call this 1, and then call this 1 ohm as well. 1 volt as well. 1 volt, 1 volt, 1 ohm, 1 ohm, 1 ohm. Okay, so because I'm not going for advanced arithmetic, I'm going for advanced understanding of circuits. All right, so can we use these? Can we use these equations or these concepts to figure out what that current is? Well, we can. So let's see what we can say. There's this first law that says that the net current going into a junction is 0. So for instance, we could call this I1, because we've got to start somewhere. And I1 goes this way, and we can call this another current, I2, except I'm not going to call it I2 because I'm actually going to want to solve for this current. So I'm going to say, I'm going to call this current I2, and then this must be whatever the deficit is, right? So that would be I2 minus I1, because the sum of these currents need to be 0, right? So I1 plus I2 minus I1 gives you I2. Similar here, this is an I2. And then outgoing here are those two same currents, because this current doesn't have any branches in between. All of the charges that go through here, they might gain some energy here, they might lose some energy here, but there's none of these charges are lost. So they'll go this way. So this is I2 minus I1, and this, let's call it I1. Okay, so we figured out the relation between the currents. Now, the sum of voltages in closed loops equals 0. Okay, well, let's do a loop number 1. Loop number 1. I apologize. That's the Roman 1. So loop number 1. And come on. Loop number 1. All right. Let's start here. The voltage going from here to there goes up by 1 volt. So 1 volt. And I'm going to drop the units because I'm going to assume that all the units make sense. So 1 volt, then I go through this resistor. My voltage is going to drop through Ohm's law by I times R, and I happens to be I1 and R is 1. So this is minus I1. And then I go through here, and it's now dropping by an I2 times 1. And then I'm back here, so the sum of these voltages is 0. All right. So I'm going to let you work on number 2. So we take a stroll through this circuit from here through there. So potential goes up by 1. Then we go through here, the potential drops by 1 minus this. So that's going to be 1 minus I2, and then of course plus I1. And then we go through here, it's going to be minus another I2, and that's 0. So that's going to give you 1 plus I1 minus 2 I2 is 0. All right. So this is not too hard to manipulate. You can just take this equation and this equation. You see there's an I1 in both of them. So add this to this. The I1 is going to cancel. You're going to get the I2 that you want. So you'll have 2 minus 3I2 is 0. So therefore I2 is 2/3 of an amp. And of course we can also use the Kramer's rule. So let me show you that. Hang on, there's a question. So there's another way to do this, and that is to not use the I1, the I2, and the I2 minus 1 right away, but to actually write this current, the I2 minus I1, as a third equation. So we have here 2 equations with 2 unknowns, and these equations are linearly independent. So there is a definite solution, so we can find that. We can use Kramer's rule, or we can use this one. Or if you don't like this, you can say, I can write a third equation. So the third equation, so number 3, it's not the third loop, and I can just call it I3. So I can call this I3. So this I'm now going to call I3. This I'm going to call I3. So then you have less messing around with the I2 minus I1 and everything. But now, of course, you introduce an extra unknown. So what we know is that I3, if it goes this way, and I1 goes this way into the junction, and I2 is the only one coming out, that means that I3 plus I1 equals I2. So you could use this as an independent third equation, and then start manipulating equation number 1, 2, and then number 3 to find the solution for I2. Except I think that's needlessly complicated. You could also set up a Kramer's rule problem for this, where you say, okay, I'm going to make this into a 3x3 matrix, but every equation that you add adds one part, one row and column to the Kramer's matrix, which means that the determinant is going to be more and more tedious to calculate. So I usually don't write this as an independent equation, I usually work this out on the diagram, because then that means having to do less. But you could do it this way, or you could just say, if you don't like eyeballing and picking what this thing is without doing the intermediate step, you can call this I3, and you could just solve for I3, and we're going to call this I3 is I2 minus I1. Okay, so now you know that this is I2 minus I1, and you can keep going. All right. So the second way to do it is with Cramer's rule. So Cramer's rule says that if you write this as a system of equations of the form AX equals B, then X, and this is a vector, and then this would be a matrix, then the X that solves it is going to be the determinant. So X1, for instance, is going to be the determinant of A1 over the determinant of A. So in this situation, we would have to write it in this manner, equals, okay, so this would be I1, this would be I2, and now we're going to take equation number 1, that's this one, and we're going to put that in the first row. Oops, not through the I1. So whatever we're going to multiply with that are the elements here are going to come from here. So we have a minus I1, so that goes here, so that would be a minus 1, because if you multiply this, you have to put this on top of it and multiply it. And then you have a minus I2, so that's a minus 1. And then we have to work this thing over to the other side, so that's a minus 1 as well. We could change the signs, but it doesn't really matter. And then the I2 was this one. Sorry, the second equation was this one. So there's an I1 that is a 1. There's an I2, there's a minus 2, and then the 1 again goes to the other side, minus I1. And now we want to know I2, so I'm going to put that here, because I'd like to have the whole thing. It's going to be the determinant of A2 over the determinant of A. Okay, that's the determinant of A2, where we take the second column, that's this one, and we replace that with the entries on here. So that becomes the determinant of minus 1, 1, minus 1, minus 1, divided by minus 1, minus 1, 1, minus 2. All right, so that's 1, that's 2, and then this is 2, 3. All right, so minus 1 times minus 1, that's 1, minus 1, so 2. It's a love fest for all the minus signs aficionados. So minus 1 times minus 2, that's going to give you 2, minus 1, that's going to give you 3. Done. So I made this comment before, but I'm going to do it again. Cramer's rule is really useful, because it's the hardcore way to give you a solution if you don't like manipulating equations this way. Because I want to tell you, when I was studying linear algebra, I'm sure you've had the same equation, same thing. Before I was studying linear algebra, whenever I would have sets of equations and it was more than 2 or 3, I would invariably get stuck in a loop. So I would, for instance, use one equation twice, and I would get an answer. I would get an answer like 0 equals 0, and that's of course not very useful. Okay. Okay. Now I'm going to teach you a little trick that doesn't always work, but it is really, really nice if you can see it. So I don't know if you noticed this, but this battery here is the same on both sides. So what I can actually do is I can actually move this battery anywhere on this branch as long as the equations remain unchanged. And I can do the same thing with this. Now, the cool thing is, because these batteries are the same, I can actually move this battery here, and I can move this battery here. And now that means that I've replaced these two batteries by a single battery in the middle. And I would have not changed any of the current laws, because the current junction rules are the same no matter where these batteries are. And these circuit voltage rules are not the same either, because no matter which path I take, I go through here, I will cross this battery once, independent of whether it's here or whether it's here. I can go in this loop, I can cross this battery. Instead of having it here, I can put it in there. And if I go in this loop, if you want to, you're going to go down plus -1. So there's effectively no voltage increase. And that's fine too, because if the battery's here, there's no voltage increase. So no matter which path you take, the circuit is completely equivalent if you move this and this to the central branch. And now you actually have a very simple circuit. So you have this one, this one. I'm drawing it small because I'm running out of space. So there you go. So now it is actually a very simple diagram. It's this one, it's reversed, but it doesn't matter. And there's one resistor, and then there's two resistors in parallel. And the current I want to know is the current in this branch. That's this current. And if this is one, this is one, and this is one, the equivalent resistance of this is 1/2. And the equivalent resistance of this is 1. And then you can just work out what the current is. Yeah. So you could totally do that if you want to. But it's a little bit of an advanced trick. Okay. Yeah, so the total resistance is 1.5 ohms if you work it out. So therefore I is 1 over 1.5 is 2/3 amp. Same story. All right, so that's advanced circuits. All right. There's one more thing I want to discuss before we go into capacitors, and that is the difference between shorts and closed and open circuits. So I'm going to draw one diagram like this. And I'm going to draw this like this. And there's a switch here. All right, and in this case, there's a switch here as well. So in this case, this part has moved in this direction, so it's now this direction, and then finally the other, where this is now connected. So this thing has moved down. Oops, battery. These are still here. So these are three different different configurations for basically the same circuit, adding switches and therefore ideal wires to this thing. They are sometimes named incorrectly, so I want to discuss that a little bit. So the first one is oh, sorry, this is wrong. The first one is this one. This is what we call an open circuit. So this switch is open because there is no current to flow through this. For instance, if you've done this experiment with the the power supplies and the resistors in 220B lab, sometimes when we use the milliamp fuse, when it blows up, it basically breaks this connection. So the ammeter is here, and therefore there's no current that flows. So if you measure the voltage across this resistor, you're not measuring anything. So this is what we would call an open circuit. And the name open is a little bit ambiguous, right? It's a little bit like saying, you know, when you have a bridge over a river, and if the bridge is open, it's actually closed for traffic, but it's open for boats to go underneath. So it's that we call this open just because we call it open. So this is what we call closed. So there's a closed contact, and this is what we call a short. Okay, so this is a short circuit, that's a closed circuit, and that's an open circuit. So something about names. All right, so an open circuit can be classified as basically R going to infinity. A closed circuit means this R goes to 0, but that doesn't necessarily mean that the entire thing goes to 0. And short circuit means that you bypass something that before had resistance with something that has no resistance. So in this case, this would be quite dangerous to do, because now you have a discharge path for the battery through an ideal wire, and that's a surefire way to either blow up your wires or blow up your battery or blow yourself up. It's short circuits are not cool. Okay, so shorts, there you go. Capacitors. I want to start with a very simple configuration. So I'm going to assume that we have a conducting plate here, and another conducting plate there, and we're going to connect this with a battery, and these are both conducting, so therefore the charge carriers are free to move from here through the wire to the other one. So what happens is if there's a positive charged carrier here, it is going to make its way through the power supply because it wants to go to the other side, and that means that there's a current that's going to flow this way, and the current is a flow of positively charged particles independent of what is happening microscopically. We talked about this last week. So if this current goes this way, that means there's going to be an accumulation of positive charges here. So this thing is going to become positively charged, and this thing is going to be negatively charged. So the next thing we need to ask ourselves is, okay, where are these charges going to sit? So if we're considering the point here, you know, nicely far away from the edges, if you're a negatively charged particle, you'll want to get close to here because you'll be closer to the rest. So what happens is all of the negative charges will go to this inner plane mostly, and all of the positive charges will go to this bottom plane mostly. So the positive charges are going to sit here. I don't know why I'm using red for positive charges, but okay. So it sits in a plane here. And the negative charges are going to accumulate here on the surface. All right. And let's not talk about the edges yet. So let's assume that these plates are so large that we can consider them almost infinitely large. And in that case, we can assume that the electric field here is going to be uniform. So so infinitely large plates would automatically lead to a uniform electric field. And uniform electric field, that means that we can draw field lines here. So let's draw them. And field lines point always from where to where? Positive to negative or negative to positive? And if you don't remember, how do you remember? So imagine you're a positively charged test particle and you're going to sit here. If you're positively charged, you're going to be repelled by this, and therefore you're going to be moving in this direction, and that's going to be the electric field line. So always from plus to minus, because that's what positive charges would do. So there's an E field. There you go. So that's the E field. Okay. The next question we can ask ourselves, okay, how large is this electric field? Well, we know what it is for a uniform field, because it's always going to be sigma over epsilon naught, except with the following caveat. So before, when we were doing the field of an infinite plane, we were taking a box, and we were putting this Gaussian box around this charged plane, and we had an electric field on the top and an electric field on the bottom. In this case, that's not the case, because of the presence of this other charged carrier on the other side. All the positive charges sit only on this side and not on that side. So when we do a Gaussian surface here, there's no flux that goes through the top surface. There's only flux that goes through the bottom surface. So that means that, and I'm going to draw a cross section because it makes it a little bit easier to draw. So this is the negatively charged and now the field. So before, we had a Gaussian surface that was sitting like this. And we had, like I was saying, there was an electric field here that was going through, except in this case, we don't have that, because the presence of this negatively charged conductor pulls out the positive charges to the side. So there's no more field on this side. So Gauss's law says that flux is EDA is Q enclosed over epsilon naught. So in this case, the E field is the E field on this side. So let's call this little surface A. That's the only part that contributes to the flux, because this surface and this surface, let me get my box again, same thing we were doing before. So the surface on the bottom here is the only thing that contributes to the flux, because there the normal is in the same direction as the electric field. This one does not contribute to the flux. The one in the back doesn't contribute to the flux. This one, etc. So only this one. So the flux is just going to be E times A on the left-hand side. So E times A. And Q enclosed is going to be whatever Q is sitting here in this box. And that's going to be Q enclosed over epsilon naught. Okay, so solve for E. So E is Q enclosed over epsilon naught. All right. Sorry, Q enclosed over A over epsilon naught. So Q over A looks like surface charge density, right? This is coulombs, this is square meters. So this we can rewrite with sigma over epsilon naught. And that means that we're going to say this one has a plus sigma. And if we do the same thing for the bottom, if you're particularly masochistic, you could do the same thing. You'd have a negative sigma here, same exact sigma, because whatever charges ended up on this came at the expense of the same number of charges on this side. So this becomes equally charged, but with the opposite sign to this charged object. And then you could do the whole thing again. You could say, flux is EDA. Now flux is going in. So therefore this flux is negative, but Q enclosed is going to be sigma over epsilon naught, but that's also going to be negative. So the two minus signs will cancel. You'll find the same field. Okay. So long story short, that's sigma over epsilon naught. Now, the next part of a capacitor is what's the potential difference? Well, the potential difference is going to be whatever whatever E is times dl, right? So delta V, let me draw delta V. So it's the line integral of E dl. So in this case, the electric field points in this direction. So therefore, the potential is going to increase from here to there. Oh, sorry, minus. It's going to decrease. That's why I was like, okay. It's going to decrease from here to there. So therefore, the potential is going to be higher here. So this is going to be at plus V, and this is going to be at 0, if you want to look at it that way. Then the line integral of EDL is going to be, if we take it in this direction, it's going to be E times D. And D is the distance between the plates. All right, so D is the distance between the plates, E times D. All right. And if we take this path correctly, we'll find something that is positive. All right, now E times D, we can express as, using these E, we can do this as sigma D over epsilon naught. And sigma is the total charge density on that surface. So if we call these surfaces big A, so these are all big A, these are all big A, then sigma is Q over A, so that's going to be Q, total Q, times D over epsilon naught A. All right. The thing I wanted to show you was that this voltage difference between the top and the bottom is proportional to the charge stored on a capacitor. But this is where we need to start being a little bit careful. So I'm going to draw the electric symbol for capacitor. So I'm going to draw this. This is a capacitor. So it looks just like a battery. So if you're not particularly careful, these are supposed to be the same. And of course, they choose the symbol because it looks like a parallel plate capacitor, which is the most easy way to build a capacitor. Then in that case, one is going to be at some voltage plus V, and the other is going to be at some voltage 0. And the charge is going to be plus Q and minus Q here. So there's a net charge difference between here and there of 2Q. So you might end up with factors of 2 if you're not careful about how you define this. Now, for capacitors, there's a quantity called capacitance. So capacitance, and we'll use the symbol C for that. And units of C are farads, short for Faraday. And it is defined, C, as Q over V. Q over V. All right. So in this case, Q would be that over V. So that would be Q times epsilon naught A over D over Q. So the Q's cancel because that's the entire point. So our capacitance is epsilon naught A over D. So that's the capacitance of a ideal parallel plate capacitor. This kind of plays the same role as the resistor that we were talking about before. So we had the resistor R, resistance R, was some function of the resistivity and then the geometry of the device. So in this case, it looks a little bit similar. There's a there is a capacitance. Hang on a second. There's a capacitance, and this is farad, or for Faraday. Sorry. Farad for Faraday. So it plays the same role as the resistance in Ohm's law. So think about the following: you can apply a voltage to a resistor, and then you get a current as a result that is proportional to something that's called R. And that R, that's the resistance, is a function of geometry and material constants. And now in this case, you can apply a charge or a voltage for capacitor, and you're going to get a resulting charge that is going to be inversely proportional to capacitance. So, and capacitance again is a function of geometry. So this C is supposed to capture the geometry and the medium, because there's an epsilon naught, and the rest goes into Q. So we factor out the Q dependence, and then we get we're only left with the thing that only depends on geometry. So this is an ideal capacitance, obviously. So now let's make some generalizations. So this is a parallel plate capacitor, but we can make a capacitor out of anything, really. So we can make some kind of a blob and another kind of blob, and let's make them both out of conductors. So conductors, and let's charge one by pulling charge from one to the other. So that means that this one's going to become positively charged. Now in this case, the positive charges are again going to try to get close to the negative charges. So they spend most of their time between this gap. And any kind of conductor that you can describe as any kind of assembly that you can describe as two conductors insulated by some kind of a gap, you can call a capacitor. So that's the most fundamental building block. So capacitance, a capacitor, is two conductors separated by an insulating gap. And I'll talk about the properties of the insulator in a little bit. And there are, this is not a super strict definition, because you can also have a capacitance when there's a resistor in between. But let's not make things too complicated right now. And now the question is, can we always say that there is some C which is going to be Q over V? Well, all right. So V would be the voltage between here and there. And Q would be the charge. So this one would be plus Q. This would be minus Q. And now the question is, can we always say this? Well, yes, indeed, we can, because we can always take a Gaussian surface. So let me take a Gaussian surface here. And Gauss's law will say that the electric field at this location is going to be proportional to the charge stored on this capacitor. We might not be able to actually evaluate what that number is, because this geometry is highly irregular, but there will be an electric field. And let me draw the field lines. It will be going something like this. Something like this. So, so there will be an electric field here, and at that location, the electric field is going to be proportional to Q, because the flux is going to be proportional to Q. All right. So because the electric field is proportional to Q, when we take the integral of the electric field over a distance, that too is going to be proportional to Q. So that means that voltage is going to be proportional to Q. So therefore, if you take Q divided by the voltage, you're going to get something that depends not on Q anymore. Okay. So because E is proportional to Q, V is proportional to Q, and therefore C is not proportional to Q anymore. So therefore, it makes sense to define the capacitance in this manner. All right. Now let's talk about the process of charging this thing. So there is a moment in time where we have a capacitor, and at t is equal to 0, we connect at t is equal to 0, we connect this battery to this capacitance. And now the question is, how much energy is going to be charged, stored on this capacitor? Well, for any kind of incremental amount of potential energy, the increase in potential energy is going to be some infinitesimal du, which is going to be V times dq, right? Because Q times V is U, so therefore V times dq is du. So therefore, U, or the potential energy stored on a capacitor, would be V dq. Now V is Q over C, so I'm going to write it as little q, Q over C dq. And now we're going to integrate that. That's going to be half Q squared over C. So that's the energy stored on a capacitor. All right. So that is once we have this at Q. So we have this at plus Q, we have this at minus Q, and then there's some E here, and this E is going to give you exactly what that V is once equilibrium has set in. All right. Now the process of charging a capacitor is I mean, we assume that right away equilibrium had set in, but it might take some time. So if we're charging a capacitor, we start initially some kind of resistor and a capacitor, and we're going to charge this thing. So at t is equal to 0, Q is 0. So when this thing starts charging, there's going to be some kind of a current flow. Those are the positive charges that this battery is going to pull from the, pull this out. Those are the positive charges that this battery is going to pull from this conducting object. It's going to put them over there. So, so we can use, again, our Kirchhoff's loop rules to figure out how that happens. So if we go in a circle, then this E minus I times R minus the voltage on a capacitor, the voltage on a capacitor is going to be Q over C, and then we're back to 0, it's going to be 0. Now, you you might not see this right away, so that's why I'm going to help you a little bit. This current is, of course, related to another quantity in this equation, and that quantity is Q, because the current is dq dt. So we can actually write this as Q dot R minus Q over C is equal to 0. And the dot is the time derivative. All right, so dq dt. And now we have a very straightforward differential equation. Q dot equals, let me bring the other one to the other side, is B minus Q over R So that's a very simple differential equation. And I'm going to let you work on solving that for a little bit. All right. I'm assuming most of you know how to do this. It's not that complicated. You should have a Pavlovian response that as soon as you see something like a first order and a second order with a minus sign, you're going to find something with an exponential solution. The thing that makes it a little bit trickier is getting rid of this E over R. It's not too hard to get rid of that because you can just substitute my whatever you want to call it, make a new variable or a new function q prime, and then that q prime is going to have that extra b, such that when you take the derivative, that b is going to drop out. So you won't have a b on the left, but you'll have a b on the right because q is now containing a minus b. So you substitute that in there. Good. Same thing. And now we are trying to get rid of this term e over r. So we do that by making this term go to 0. When we do that, by choosing the appropriate b, and we can totally do that. But we choose b as e over c. So now we have a very straightforward first order differential equation. We've got a q dot is equal to q over rc with a minus. Because there's a minus, and that means there's a minus in the exponent, and this is the thing that shows up with the chain rule. So these are the types of differential equations you should be able to solve. Anything more complicated than this, you can probably expect in a different course than mine. Okay, so then finally, we have our general solution, but we don't know what that prefactor is. And then we use the boundary condition that initially this thing was not charged. So then that means we get this E over C. So now the nice thing is that you get this Q as a function of time goes from 0 to the full charge with some characteristic time, RC time. That's the characteristic time, right? Because that's the thing that divides this. So after one time of R times C, this thing is at 1 over E away from its final equilibrium value. But this RC time is a very important concept. We will talk about this a lot when we talk about when we talk about AC circuits, and then you'll see this RC thing show up everywhere. All right, and now let me go back to the thing. Okay, so capacitors and the energy stored on them. So two things I want to say about this. So the first is that capacitors, because you can store energy on them, are really interesting elements to consider for using for energy storage. So you might know that electric cars, one of the hardest things about making electric cars cheap and giving them long range is having really good batteries that can store a lot of charge, and you can discharge quickly. And the problem with most electrochemical batteries is that when you discharge them a lot and you charge them a lot, you're changing the electrode structure, and after a while they kind of go bad. Sadly, that's it's a problem. Now, the nice thing about capacitors is that you can charge them and discharge them really fast because you're not doing any electrochemistry on the surfaces, so they just stay metals. And you can store energy on it, as we have just described, except the problem is that you can't really store a lot of energy on it. So there's been a lot of work in trying to figure out how you can build capacitors that can store energies as well, and I'll explain what I mean by well, as batteries can. And since the capacitance goes by epsilon A over D, one thing you could do is put the plates really, really close together. And turns out that in electrochemical cells, if you build them properly, you can actually get the counterions and the metal so close that that constitutes capacitance. And now you're talking about supercapacitors. So they're sort of a hybrid form of capacitors and electrochemical cells. It's one of those things that are actively being researched, and there's many versions of this, and I'm not an electrochemist, so you'll forgive me if I'm going to skip the details. But meanwhile, back at the point, capacitors, really useful. So there was a while back, there was a company that was selling ultracapacitor or supercapacitor based power drills. which is really nice because I don't know about you, but whenever I need a power drill in my house, at that point it's always discharged, and it takes half an hour to charge. This thing, because it doesn't do any electrochemistry of the surfaces, you could charge it in 30 seconds flat, which is really nice. So unfortunately, that means as soon as there's a problem in a house, you are on the clock. So you have to fix it right away. The other thing I wanted to mention is capacitors. You have probably seen this mentioned when you have cell phones and iPads. The screens are called capacitive touch screens. So I need to explain to you what the capacitive there means. So actually, what a capacitive touchscreen is it's an insulating glass with metal pads on the top and the bottom, and these metal pads, they all make little capacitors, but the metal pads are a little bit offset. So there's one here and there's one there, and you charge this one positively, you charge this one negatively, then the field lines are going to go do this. Now, when your finger gets close, you're going to charge your finger a little bit. So it's going to change the field lines. And if it's changing the field lines, it's going to change the capacitance. So if you're monitoring the charge, you can detect that. Or if you're monitoring the potential while holding the charge constant, you can detect that. And that's how a touchscreen sees where the screen is being touched, because this glass is actually, it's got a complete grid with conducting pads on the top and the conducting pads on the bottom, and it intermittently scans the pairs to figure out which ones are being activated by putting your finger close to it. And that's how capacitive touchscreens work. So, oh yeah, I should mention. So these are transparent conductors. So that's why you can actually see through them. Very common transparent conductors, indium tin oxide, and that's an entirely different subject, but yeah, transparent conductors. All right, with that, I want to thank you for your attention. I'll keep the chat open for a couple of more minutes if there's more questions, and otherwise, of course, there's office hours as well. Thank you, everybody.